All right, so lesson 2.5, zeros of a polynomial function. So we started kind of dabble with this as, last time we did dividing polynomials, and sometimes that ended up giving us a factor, which we could then find the zero for. But we could also find the remainder, or use the remainder to find what, say, f of a particular number is, in this case f of 2. So synthetic division, I'm going to put the 2 in there. So x to the third would have a coefficient of 1. X squared is a minus 4. X is a plus 5. And our constant is 3. So bring the 1 down. 1 times 2 would be 2. 2 and negative 4 is negative 2. Negative 2 and 2 would be negative 4. 5 and negative 4 make 1. 1 times 2 would be 2. 2 and 3 make 5. So 5 being the remainder is what f of 2 is. And we're going to move on. So, working with polynomials that are higher than a quadratic. So, these are ones that are not going to be ones we can just look at and go, oh, well, I know one factor and how this breaks down. Much more complicated, so here's some methods on how we find those zeros. So first off, we have our rational zero theorem. What this is going to allow us to do is find what zeros are possible. And what they do is they're looking at, they're going to use P over Q here. P is the factors of the constant term. So whatever our constant is, whatever factors we could have, is going to be there. So think of this one, we're going to call it our C, just to make it simple. C, constant. Q then is going to be our leading coefficient. So again, there, let's make this an L. So C and L is what we're going to work with, so that would make it C over L to get our possible zeros. So those possible zeros, factors of our constant over the factors of our leading. So again, C over L. So what we're going to do is, you start by listing all the factors of the constant term. Then we're going to list all the factors of the leading coefficient, and then we're going to make what's possible there with these fractions. So list the possible rational zeros of f of x equals negative x to the fourth plus 3x squared plus 4. So we have our leading one, we have our constant one. Leading, the only thing that we're dealing with is a negative 1. So the only thing that's possible would be a plus or a minus 1. So I'm going to put the negative 1 in front. How about that? My constant, though, is a 4. So factors of 4 could be 1 and 4, or it could be 2 and 2. So each of these could be positive, could be negative. So when I set this up, I'm going to do C over L. So 1 over 1 could be positive or negative. 2 over 1 could be positive or negative. And 4 over 1 could be positive or negative. So what we have here is plus or minus 1, plus or minus 2, and plus or minus 4, if they're all over 1. So these are our possible zeros. Now, later on we're going to go through, once we have them, what's going to happen. But before we do that, let's do one more. So we're going to list all the possible rational zeros of f of x equals 15x to the third plus 2x squared minus 3x minus 2. And we're getting fuzzy there. Sorry about that. That looks better. All right, so again, leading, constant. So possible for my leading. Well, my leading is 15. So factors of 15 would plus or minus 1, plus or minus 15, plus or minus 3, plus or minus 5. For my constant is a negative 2. So sign doesn't matter so much as what our number is, because the sign's going to be covered with the plus or minus. So with 2, the only factors would be plus or minus 1, plus or minus 2. So when we set this up as our possible, we would have plus or minus 1 over 1 plus or minus 2 over 1. And we go to the next one. So plus or minus 1 over 3 plus or minus 2 over 3. Go to the next one. Plus or minus 1 over 5 plus or minus 2 over 5. Plus or minus 1 over 15 plus or minus 2 over 15. So 1 over 1, well, we can simplify that to 1. 2 over 1, 2. Now, what we're kind of doing here is we're kind of looking, okay, is there any repeats here that we don't need to mark again? Well, 1/3 doesn't match any of these. 2/3 doesn't match these. 1/5 doesn't. 2/5 doesn't. 1/5, yeah. So we're going to list these all out. So plus or minus 1/3, plus or minus 2/3, plus or minus 1/5, plus or minus 2/5, plus or minus, oh, not there, there. 1/15, plus or minus 2/15. So these are what's possible. Now, obviously, as you go about this, you can go, well, if I know, I'm going to know if I put it over 1, I'm just going to get the 1. So same thing here. If I put it over 1, I'm going to get the 2. So to save you writing all these out a second time, you can skip that part and just go right to it. But this is just the listing all what's possible. So if you think about it, there's 2, 4, 6, 8, 10, 12, 14, 16 different zeros that are possible with this one. Now, how do we start narrowing them down and checking? Well, you're going to use synthetic division to do that. So each of these is what's going to go in the box, and you're going to use the coefficients of the original function. And again, remember, it has to equal 0 for a remainder for it to be a function. So we're going to check all the zeros with this one. So to start off with, our leading is just 1, so plus or minus 1. Our constant here is a -6, so we could do plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So 1 times 6 or 2 times 3, factors of 6. So as far as what's possible, RC over L, well, all of these are going to be over 1, so it's just going to be these. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So in this case, we have 2, 4, 6, 8 different possible zeros. So what we're going to do is we're going to start checking stuff. So I'm going to start with 1 in the box. So we have 1, 2, -5, -6. So 1 times 1 is 1, 2 and 1 is 3, 3 and 1 is 3, so -5 and 3 would be -2, -2 is -8. So it doesn't work. So I'm going to go on to 2. So again, we have 1, 2, -5, -6. So 1 times 2 is 2, 2 and 2 is 4, 4 and 2 is 8, 8 and -5 is 3, 3 and 2 is 6, and hey, we got a 0. So from there, once we get this down, remember, this is your quotient of what's left. So x squared plus 4x plus 3. Now, you don't have to keep doing synthetic division with this stuff. If it gets to where you can factor it, just go ahead and factor it. Don't keep doing synthetic division. Now, if this is a big enough number, you're like, oh, yep, I still can't factor it, then use those coefficients, the 1, 4, and 3 in this case, and then keep doing the possible zeros. Now, if you've already done 1, you're not going to need to do 1 again. If 2 works for this one, you're not going to do 2 again here. So do new ones that you haven't done. But obviously, if you get it to here to where we can factor it, so like this one's going to go x plus 1, x plus 3. So we know 2 is already one of them. Here, if we set this equal to 0, we would get x equals -1, -3, and then 2 is our other one. So we'd have our 3 zeros then. So you go through, check it with synthetic division. Once you get a remainder, see if you can factor that. If you can, factor it and solve it. If you can't, then do synthetic division again. So we're going to find all the zeros here. So again, this is our leading, this is our constant. So leading is a 1, constant is a -3. So factors of 1, just plus or minus 1. Factors of 3 would be plus or minus 1, plus or minus 3. So again, all these are C over L is going to be over 1. So it's just going to be plus or minus 1, plus or minus 3. So here we only have 4 to check. So if we start with 1 in the box, we could do 1 for the x to the third. X squared would be 7, 11, and -3. So 1 and 1 is 1, 7 and 1 is 8, 8 times 1 is 8, 8 and 11 make 19, so the 19 goes up there, 19 and -3 is 16, so again that one doesn't work. So let's try the 3 then. So for now I'm going to do the positive ones first, and then we could go through and try the negative. That's just one way to do it. You can come up with your own style with this of how you choose which ones to try. I'm just doing this just because. So my 3 here now, we still have our 1, 7, 11, -3. So 1 times 3 is 3, 3 and 7 is 10, which makes 30, which makes 41, which makes 123 is 120. So neither of the positives work. So on to the negatives. 1, 7, 11, -3. So 1 and -1 is -1, which makes 6. Minus 6, 11 minus 6 is 5. -5 is -8. And of course it would come down to the last one. So 1, 7, 11, -3. Let's bring the 1 down. -3 and 7 is 4. 4 and -3 would be -12, which would be a -1. -1 and 3 would make +3, which gives us 0. So -3 is the solution. We have x squared plus 4 minus 1. Now, this one, not so factorable. We're also out of possible zeros to try. So what that tells me is the last 2 zeros here, because we're x squared, are going to be imaginary numbers. They're not going to be real numbers. So if we do quadratic formula to show this, the other 2, so our 1 is going to be x equals -3. So we found this one. So Pythagorean theorem would be x equals -b, so -4 plus or minus the square root of 4 squared, 16, minus 4 times 1 times -1, which would be a plus 4, over 2 times 1. So in other words, -4 plus or minus the square root of 20 over 2. 20 I could break down to 4 and 5, which goes to 2 and 2, so I can pull a 2 out. And so x would equal -4 plus or minus 2 square roots of 5 over 2, which would reduce to x equaling a -2 plus or minus square root of 5. Okay, so this one didn't end up being imaginary numbers, but square root of 5, not a nice number to work with. So these are possible. Again, they're not necessarily all, because we could get decimals in here. But in this case, one of them worked out. We were able to find the other 2 this way. Now, if we're bigger polynomials, like I've said before, we can complete or continue this process so that you can keep breaking it down further. You would just try more of these what's possible. So that's what I'm saying here is we can repeat it for bigger polynomials. Now, properties of polynomial equations is if a polynomial equation is of degree n. So in other words, we're going to have multiple roots all going on. So it's whatever its degree is how many roots there's going to be. Now, if there is a complex root or an imaginary root, whatever you want to say, a complex imaginary number here, they always come in pairs and they're always conjugate. So if one is a plus bi, it would have another root of a minus bi. So imaginaries are always in pairs. Fundamental theorem of algebra there. So if f of x is a polynomial of degree n, where n is greater than 1, then the equation f of x equals 0 has at least one complex root. So as long as we are bigger than 1, there's going to be at least one that's complex, is what this is saying. If we can set it equal to 0 and solve, basically. Linear factorization theorem. So what this is saying is this. To get this here, when you multiply it out, it's going to be in this form of a sub n, which could have been a common factor, common multiple that you would have pulled out front. And then these are the factors all times each other. C1, C2, C sub n. Those are all zeros that you would come up with. So, I'm trying to think if we do this one next. I would assume so. Okay, so we do one next. So I'm going to show you where this is going to come from. So find a fourth degree polynomial with a real coefficient that has -2, 2, and I as zeros, such that f of 3 equals -150. So this, keep in mind for later. But to set this up, f of x equals our a sub n times x minus our 0, so this one would be a plus 2, x minus the next 0, which would be a 2. Now, because there's I, we know we have to have x minus I and its conjugate x plus I. I's always come in pairs. One's a minus, one's a plus. From here, we're going to multiply stuff out. So equals a sub n. So x plus 2, x minus 2 would go to x squared minus 4. So these are a difference of squares. So x and x squared. You'd have a plus 2x, a minus 2x, so the middles would cancel. 2 and -2 make -4. For this other one, same idea. We would get x squared minus I squared. Remember, I squared, though, is -1, so that's going to cancel and be, I'm going to rewrite it over here, x plus 1, x squared plus 1. So, FOIL these two now. So x squared times x squared would be x to the 4th. X squared times 1 would be plus x squared. -4 times x squared would be a minus 4x squared. -4 and 1 would be a minus 4. So these two I could put together, and so we have a sub n equals x to the 4th minus 3x squared minus 4. So we still have this a sub n, which is where this comes in. So this is saying when x is 3, we're going to get a -150 out. So if I do f of 3, I'm going to have a sub n times 3 to the 4th minus 3 times 3 squared minus 4, all equaling 150. -150, sorry. So -150. So a sub n, 3 to the 4th. So 3 raised to the 4th power is going to be 81. So 81 minus 3 squared would be 9. 9 times 3 is 27, and then minus 4. So if we put these together, 81 minus 27, I should know off the top of my head, 54, minus another 4 leaves us with a sub n times 50 equaling negative 150. So you get a sub n by itself, you would divide by 50 then. So our a sub n would equal negative 3. So that was a common factor that would have got pulled out up front. We can put it back here. So our f of x is equal to our a sub n, which we found to be negative 3. The rest of this here, x to the 4th minus 3x squared minus 4. So we distribute it in. So our final equation, negative 3x to the 4th, negative 3 and negative 3 would be plus 9x squared. Negative 3 and negative 4 would make a plus 12. Would be the final answer. So we have the zeros. Basically what you're going to do is put them into that form of x minus whatever the 0 is, and then you multiply them out. Once you have them all multiplied them out, use the information they give you, then define your a sub n, distribute your a sub n in, and that's your final equation. So again, as you're going through these, if you have questions, please ask me. Remember, you can always pause it if you need more time to write this stuff down. You can always rewind it, so move the little dot back and rewatch something if you missed it. But please, do not sit there and struggle. Please let me know if you're having trouble. Do those things to help yourself out. Now, what we have here is Descartes' rule of signs. Now, I'm probably butchering that name, and I apologize to whoever Descartes is, but that's how I'm going to say it. So Descartes' rule of sign is this. First, you're going to go through and you're going to count how many sign changes there are. So if it's this one's positive, this one's negative, that would count as one sign change. However many there are is going to be the number of positive real zeros. That's either that or less than that by a positive even integer. So you 2 on down. Then you're going to go through and put a negative x in. So how that will change the signs. And then again, you go through and count them up, how many sign changes happen. So we're either going to be that or again a positive even integer, so a multiple of 2 on down. So let's do some here and let's go from there. So positive wise, we're positive to negative, so there's 1 sign change. Still negative, positive, so there's 2 sign changes. Still positive, negative, so 3 sign changes. So as far as positive zeros that are there, we could have 3 of them, or we would have 1 of them, because we go down by 2. So 3 is how many sign changes happened. So we could have all 3 be positive, or they go down by 2s. So 3 minus 2 is 1, so there could be 1 positive. Now, if we did a negative x in here, x to the 7th would change the sign and make this negative. Same thing, odd exponents will switch the sign, even will stay the same. So, to get my negatives now, so we're negative to a positive, so that would be 1. Positive to a negative would be 2. Negative to positive would be 3. Positive to negative would be 4. And then it stays negative, so 4 are what's possible. Yeah, scroll back up here. 4 is what's possible for the negatives. So we could do 4 or 2 or 0 of them. So if you think about it, there are 7 x's here. So we could have 3 of them positive, 4 of them negative. We could have 1 positive, 4 negative. We could have 3 positive, 2 negative, or no negatives. There's at least going to be 1 positive. So this is what's going to help you when you're determining what to really put in for solutions to check. Because if you go through and go, oh, I have no sign changes, so there can't be any positives, why are you going to check positive zeros? Skip that part. Go on to the negatives. Go with what it has. So if you're going through and you find that, hey, I have one positive, and then you don't get any more to work, hey, that's my one positive. I'm going to go on to my negatives. So this is going to help you tell which zeros to try. So again, if we go here and we look at positive, so we're positive, positive, so that's nothing. Positive to a negative, so there's 1. Negative back to positive, there's 2. Still positive. So 2 or 0 positive possible solutions. X to the 5th. Odd exponent, it would change sign. Even it wouldn't, even it wouldn't, odd it would. So if we go through now, we have negative to positive, there's 1. Positive to negative, there's 2. Negative to negative, no, but negative to positive would be 3. So we would go 3 or 1. So out of 5 of them, you're going through and you're like, man, I hit 2 positives already. Well, 2's the most that are positive, so stop doing the positives then. And I would go through and start checking my negative zeros. So positive, negative. So positive, you go through it just how it is. So negative to negative doesn't change, negative to positive, and positive, so there's only 1 there. So 1 possible positive. So out of 6 of these, only 1 of are positive. So again, if you find that 1 positive, stop checking positives, go on to the negatives. Negative as my other possible here. So even wouldn't change, even wouldn't change, odd would change. So negative, negative, nothing, negative, negative, nothing, negative to positive be 1. So 1 negative. So this is telling you right now there's 1 positive, 1 negative. There's 6 possible roots. So that tells you 4 of these have to be complex imaginary roots. So they have to have eyes in them. Only 1's positive, 1's negative. So one more here where we're going to determine the possible number of positive and negative real zeros. So positive, we're positive, 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 positive. So there's going to be no sign changes. So that right there is going to tell you when we're looking at what's possible, none of them are going to be positive. We would only go through and check negative ones as long as we have a negative one. So odd, so that would be a negative, even wouldn't change, odd, it would change, and a constant wouldn't. So negative to positive is 1, positive and negative is 2, negative positive is 3. So there's going to be 3 or 0, or 3 or 1, sorry. So this is what's possible for positive and negative real zeros. Now, these are just the signs, but we're going to determine what zeros we're actually dealing with. So we have our leading, which is going to be a 1 because we go back to the original. Our constant then is a 4. So as far as leading, we would have plus or minus 1. For constant, we could have plus or minus 1, plus or minus 2, plus or minus 4. So everything's going to be over 1. So our C over L would be plus or minus 1, plus or minus 2, plus or minus 4. Now, again, we know none of them are going to be positives. So only thing that we're going to check are going to be the negative solutions. Now, it could be 3 or we could be 1. So if we have one that doesn't work, we'll automatically know only one of them will. So first box, so I'm going to check negative 1. So my numbers would be 1, 2, 5, and 4. So bring the 1 down. 1 and negative 1 is negative 1. 2 and negative 1 make 1. So again, another negative 1. 5 and negative 1 is 4. 4 and negative 1 is negative 4. We get 0. So right there, that tells me negative 1 is going to be a solution. Now, I could keep checking, but what we have here is x squared plus x plus 4. So could I factor that out? Well, no, that doesn't come out real nicely. So I am going to try another one here just to check. So negative 2. This shouldn't work, and we're going to double check that it doesn't work, and then we would be able to stop, and this is our 1, and we know the other two are complex. So 1, 1, and 4. We already got one solution, so we don't need to put them all in. We can just put that quotient in for our numbers. So 1 times negative 2 is negative 2. 2 and negative 2 is 1. Negative 1. Negative 1, negative 2 is positive 2. We get 6. So obviously that doesn't work. So one of them is x equals negative 1. Other two are complex conjugates. I can't spell conjugate. There. J first. So, that is it for this lesson. So let me know if you have any questions. Remember, you can always go back. You can pause the video if you need to write stuff down. You can always rewind and rewatch something if you need to catch it, if you missed something. Otherwise, let me know if you have questions. And until next time, we'll talk to you later.